Welcome back to The Explainer. Today we're zooming way in to look at the literal fabric of our reality, matter and its composition. We're going to uncover the invisible physical rules that govern absolutely everything around us, from a tiny speck of dust all the way up to the largest planets.
I want you to think about this for a quick second. What do a heavy brick, a single drop of water, and the invisible air you're breathing right now actually have in common? Well, let's dive into this because the answer is basically the entire foundation of physics and chemistry. Here's our quick roadmap for today. First, we'll establish the precise definition of matter. Second, we'll hit the secret particle theory. Third, we'll look at solids, liquids, and gases. And finally, we'll explore changing states of matter. We're building this up straight from the micro all the way to the macro level. All right, Section 1, the definition of matter. Before we can get into the complexities of the universe, we got to establish the absolute ground rules for what actually makes up the physical world. So, the scientific definition is actually pretty simple. Matter is just anything in the universe that possesses mass and takes up physical space. That is the ultimate prerequisite for existing in our physical world. If it lacks either of those two things, it's not matter. Let's break down those two key requirements real quick. First up is mass. Mass is literally the exact quantity, the amount of stuff contained inside an object. There's a wonderfully simple analogy for this. Think of a box filled with traditional Indian sweets like laddus. The mass of that entire box depends entirely on the specific quantity, the actual number of laddus inside it. Mass is purely about quantity. And the second requirement is volume. Volume is the exact amount of three-dimensional space that an object occupies. Just think about your everyday water bottle or, the soap dispenser sitting in your bathroom. Whether that dispenser holds 500 milliliters or a full liter, that physical capacity, the space it literally dictates and occupies, that's its volume. Okay, now that we've defined the big stuff, let's move on to Section 2, the secret particle theory. We are taking out our microscopic lens to look at the tiny building blocks of matter. It turns out all matter is constructed from extremely tiny, completely invisible particles that are constantly in motion. Constantly. Whether you're holding a heavy bar of gold, a glass of water, or just a handful of sand from the beach, it is all made up of these distinct, incredibly small particles. You'd need a seriously advanced microscope to even stand a chance of spotting them. And this brilliantly illustrates the two hidden forces at play in literally every single object in the universe. We have interparticle space, which is the actual physical distance between the particles, and interparticle force, which is the invisible bond locking them together. Now, these two operate in a strict inverse relationship. As the space between particles increases, the force keeping them together naturally drops. There is a wonderfully relatable way to conceptualize this. Think of interparticle force exactly like a friendship. The more space you put between friends, the weaker the bond tends to become. Right? If you move to a different city, the physical space grows, and without putting in the effort, that friendship bond, that force of attraction, naturally weakens. Matter acts exactly the same way. Proximity creates the strongest bonds. Let's move to Section 3 and see how this builds our understanding of the macro world. We're taking those invisible roles of space and force and applying them to the three physical states we interact with every single day. Starting with solids. Here, we find tightly packed particles with an extremely strong force of attraction. Because those friendship bonds are so incredibly tight, the particles literally don't have the room to flow. They just sort of vibrate in fixed positions. And that is exactly why objects like rocks or the metal pen on your desk have a fixed shape and a fixed volume. They're highly rigid and they cannot be compressed. The particles absolutely refuse to be pushed any closer together. But what happens if we increase that space just a tiny bit? We get liquids. With larger space between particles, we get a weaker force of attraction, and this extra room is an absolute game changer because it allows the particles to slide past one another. That sliding is why liquids flow. It perfectly explains why a liter of water will shape itself to whatever container you pour it into, a tall bottle, a wide tub, while still keeping its volume fixed at exactly 1 liter. And finally, we have gases. Massive space between particles here, which means an extremely weak force of attraction. In this state, the particles basically behave like kids let out onto a school playground, just moving wildly with total freedom in every direction. Because they are so far apart and totally untethered from one another, gases have absolutely no fixed shape or volume, and they're highly compressible. They'll just spread out forever to fill whatever container you put them in. So the crucial point to take away here is how the microscopic rules of space dictate the macrophysical properties. In solids, everything is fixed and super dense. In liquids, shape becomes flexible, but the volume is locked in. And in gases, the whole shebang is unfixed, density drops incredibly low, and they become highly compressible. Which brings us to our final segment, Section 4, Changing States of Matter. We know the rules of the three states now, but how do we force matter to break its own rules and transform from one state to another? It all comes down to energy, specifically temperature. If we start with a solid, like ice, and we crank up the heat, we're giving those tightly packed particles kinetic energy. They start vibrating more and more violently until, bam, they break those strong friendship bonds, giving them the space to turn into liquid water. Add even more heat, the bonds break further, and the particles get the energy to completely escape as gas or vapor. But hey, this is a two-way street. The cooling process works in the exact reverse by taking that energy away. Gas cooling down into a liquid is called condensation. Liquid cooling further into a solid is freezing. And get this, heat energy is actually released during these cooling steps. You see this every single day. Think about the water droplets forming on the outside of a cold bottle you just pulled out of the fridge. That's just the warm water vapor in the air, hitting the cold plastic, losing its energy, and condensing into a liquid drop. Now, what's really interesting about this next concept, the golden rule of interconversion, is that the physical state changes, but the chemical composition never does. Water is always water, whether it's a solid block of ice, a flowing river, or invisible steam. Chemically speaking, it remains the exact same substance. Temperature isn't our only tool, though. Pressure acts as the second great director of matter. Take a gas with widely spaced particles and apply extreme external pressure. You are physically forcing those particles tightly together. Because gas particles have so much empty space between them, the pressure literally overrides their freedom and converts them into a liquid. This is exactly how we get LPG cooking gas in our kitchens, or CNG for our cars. They are naturally gases, but they're compressed so tightly they become liquids we can efficiently store in cylinders. But, sometimes matter likes to take a shortcut. And that brings us to a super fascinating concept called sublimation. It's this unique process where a solid turns directly into a gas upon heating, entirely skipping the liquid phase. You've probably seen common everyday examples of this, like camphor used in religious ceremonies, or naphthalene balls in your closet to protect your clothes. They don't melt into puddles, they just vanish, going straight from a solid into a gas. This entire journey from invisible particles to complex state changes leaves us with a truly fascinating question to ponder. If adding physical pressure forces a gas to turn into a liquid by squishing its particles together, what in the world happens to the state of matter at the center of a black hole, where gravity makes pressure practically infinite? How do these physical rules of matter hold up under the absolute most extreme conditions in the universe? Keep wondering, keep learning, and thank you so much for joining me on this explainer.